This is Physics 104B Homework Solutions, Chapter 23, Porterville College. Number 13, we're bringing these four 50 microcoulomb charges initially from an effective distance of infinity brought into line, as you can see in the diagram, 2 centimeters apart. How much work does it take to assemble the charge distribution? So we have the work equals and it becomes the potential energy between every possible pair. So here I've made the distance of 2 centimeters be A to cut down on the clutter of writing. So the potential energy KQ1, Q2 over A, that's for between 1 and 2. Between 1 and 3, that's going to be a distance of 2A. Between 1 and 4, it's a distance of 3A. Then between 2 and 3 is a distance of A, and between 2 and 4 a distance of 2A, and between 3 and 4 a distance of A. So we're going to add up all those potential energies. Then I only wrote Q1 and Q2 and put the subscripts on Q just so you could see the different combinations I'm making. But in this problem, all the charges are the same, so here I say let all the charges just be Q. So we get rid of all those Q subscripts. So then we can factor out of every one of these expressions K, Q squared, and A. And when you do that, that leaves us with this one becomes 1 plus 1/2 plus 1/3 plus 1 plus 1/2 plus 1. So you add that up and you get KQ squared over A times 13/3, and then we plug in the numbers. 50 microcoulombs, that became 5 times 10 to the negative 5. Remember, you're squaring it. K is 9 times 10 to the 9th, a distance of 0.02 meters, and so what we end with is the total work is 4,900 joules. Number 14. Now this is similar, a bit more geometry to it. So we've got this square, and I've put dots for the individual points. I've labeled them here 1, 2, 3, and 4, and put their charges next to them, Q, 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 and negative 1/2 Q. That's what I've labeled particle number 4. Just as I did with with problem number 13, the previous problem, there I called it the work. Well, it's also the potential energy between any 2 points is K times the product of their charges divided by their distance. So the potential energy to assemble this, assuming they're coming from, okay, we're not finding work, we're finding the potential energy. So that's going to be the potential energy of every possible combination. And between 4 points, there's going to be 6 possible combinations. So U of between 1 and 2, U between 2 and 3, etc. So I'm going to use this expression for potential energy, and it's going to look similar to number 13, the previous problem, but as I said, the geometry is a little different. So we've got K times, between 1 and 2, that's just Q squared over A. 2 and 3, Q squared over A. Between 3 and 4, now the product of the charges is Q times negative 1/2 Q, so we've actually got negative Q squared over 2A. Between 4 and 1, it's the same thing, negative Q squared over 2A. And these last two, combining 1 and 3 and 2 and 4, those are going across the diagonal, 1 and 3 and 2 and 4. Some basic geometry, if you look at the square that my pen is pointing to, if you have a square that's A on each side, the diagonal is square root of 2 times A. So I've plugged that in and gotten those. For 2 and 4, you've got a combination of it's Q times negative 1/2 Q, so that that 1/2 appears as a 2 down here. Then your square root of 2 comes from the distance in the denominator. Now from this bracket, from these brackets here, you can factor out Q squared over A. And so when I do that, I get 1 plus 1 minus 1/2 minus 1/2 plus 1 over square root of 2 minus 1 over 2 square root of 2. And from there it just becomes a bit of arithmetic simplifying this. And you might get it in a different form, but this is the form I've left it as. KQ squared over A, 2 square root of 2 plus 1 over 2 square root of 2. You might want to get it in a form that doesn't have a radical in the denominator, but you can just check to make sure that your answer matches up with mine by a calculator. Number 16. 3 particles with identical charge and mass released. What speed will they have far away? So this is a conservation of energy problem where all of their potential energy will be transformed to kinetic energy, assuming that their potential energy all goes to 0, meaning very far away. So potential energy initially equals kinetic energy finally. Here's, just as we did in the previous problem, the potential energy of the total system. And that's going to equal the total kinetic energy. You've got 3 particles, so 3 times 1/2 mv squared. And a little bit of algebra, my 3's divided out, and you should get that velocity is the square root of 2kq squared over ma. Number 21, very straightforward, simple problem involving capacitance. Capacitance is charge divided by voltage. So 1.3 times 10 to the negative 6 coulombs divided by 60 volts. You should get 2.2 times 10 to the negative 8 farads, or 22 nanofarads. Now we have to find the capacitance. So capacitance is epsilon naught area over d. We have circular plates. We're given the radius, so I've turned area into pi r squared. So you plug the numbers in where radius is 0.2 meters. Distance is 1.5 times 10 to the negative 3 meters. And you should get 7.4 times 10 to the negative 10 farads, or 740 picofarads. Number 29. Connecting two capacitors in series and parallel. So series, I've done the simple formula, which is you can use when combining just 2 of them, and you should get 2/3 of a microfarad. Becomes 1 times 2 over 1 plus 2 microfarads. In parallel, the capacitances just add up, so 1 plus 2 equals 3 microfarads. Number 49 is a good exercise in working with how capacitors add in a variety of combinations. So we're given that all of these are equal capacitances, and what you need to figure out, what you need to discern from the picture is what combinations are in parallel and what are in series. So we see that 3 and 4, and I've labeled these here 1, 2, 3, and 4. 3 and 4 are in parallel with each other. And then that combination is in series with 2. So let's go from there. If we combine 3 and 4, they're parallel to each other, and so the capacitances add. So if this is C and this is C, the capacitance, what I've called C34, that's the combination, 3, 4, has a capacitance of 2C. So now I redraw the diagram and imagine that there's one capacitor here, capacitor 3, 4, and it has a capacitance of 2C. And it's in series with capacitor number 2. So here is the how we combine them in series. I say the series C234, and when I combine those, that'll become this one right here. But for a series of two capacitors, we have the product of their capacitances over their sum. So C2, C34 over C2 plus C34. Product over their sum. And that gives 2/3 of C. So now in this diagram, I've replaced all three of those capacitors, 2, 3, and 4, with one capacitor that is 2/3 C. Now I see that 1 and 2, 3, 4 are in parallel with each other. Capacitors in parallel add, so C plus 2/3 C, and we get a total capacitance of 5/3 C. The problem involves, they've measured capacitance per area. So we're going to take this capacitance formula and get in terms of capacitance per area. So C over A is kappa epsilon naught over D. And we want to solve that for D. So D equals kappa epsilon naught over C over A. You plug in the numbers, where C over A is 10 to the negative 6 farads per centimeter squared. We get an answer of 2.7 times 10 to the negative 5. But if you look at the units, be careful here, the units, when the farads divide out, are centimeters squared per meter. And we need this in units of one distance, one length. So what I've done here is a conversion to to get rid of one of these meters. So I've done 1 meter over 100 centimeters. And so meters and meters divide out. You're left with 1 power of centimeter dividing out. So you're left with units of centimeters. So 2.7 times 10 to the negative 7 centimeters, or 2.7 nanometers. Number 59, a cubical region, 1 meter per side. This first line here, I solve for what E is equal to, plugging in for E naught over X naught, getting 4 kilovolts per meter squared. But then I sort of changed direction as I was doing this problem, and in the end I didn't even use this value of 4. So that really wasn't necessary to do. Here's our picture, and it's a cube, but all we really concern about is changes in the x direction. So this cube, I've divided it into these slabs that are dx width, a height of 1, and a thickness of 1 coming out of the paper. So the volume of one of these little elements is the height of 1 times the thickness of 1 meter times the thickness in the x direction, dx. So the volume of each of my little slabs, dV, is equal to dx. Now be careful with the equations that you're using here. V does not stand for voltage. Here it stands for volume. Potential energy, this equation came from the book, 1/2 epsilon naught times the integral of E squared integrated with respect to volume. I've substituted in that E squared is E naught over X naught times X. So the E naught and the X naught squared, they come out to the side. All you're left with is the X squared. So we have this constant right here, multiplied by the integral of X squared, integrated from 0 to 1 with respect to X. So the integral of X squared dx is 1/3 X cubed. And in this last line, I've got the x cubed. The 1/3 I just threw out here to the side. I combined it with the 1/2, and so that's where the 6 comes from. And you integrate and you get 2.4 times 10 to the negative 5 joules. Okay, the last one, or the last four, are the passage problem involving the National Ignition Facility. So for number 75, it gives the the energy is given in the problem, 400 megajoules. And it tells the voltage, so from U equals 1/2 CV squared, where U is the 400 megajoules, we just solve for capacitance, 2U over V squared. And you should get 2 farads. Number 76, double the voltage, how would the required capacitance change? Okay, so looking back at this equation in number 75, required capacitance, so we're assuming we want the same amount of energy. If you were to throw a 2, multiply this voltage by 2, the denominator would be affected by, it would be multiplied by 2 squared, which is 4. So the capacitance would drop by a factor of 4. Number 77, what is the power? Remember, power is energy divided by time. It says that when they're firing, the passage says the lasers deliver 2 megajoules of energy. So you've got 2 megajoules of energy, 2 times 10 to the 6, over a time of 10 to the, in 1 nanosecond. Whoops, I have a writing error here. Okay, seemed a little short. 10 to the negative 9 seconds. And so what that gives us is 2 times 10 to the 15th watts, or 2 petawatts. And the last one, number 78. Among the capacitors, so it's not saying that these are the only capacitors, just among them are 1,200 300 microfarad units charged about 20,000 volts. The energy stored in each capacitor. Okay, so energy is 1/2 capacitance of 300 microfarads, 300 times 10 to the negative 6, times 20,000 volts squared, and we get 60,000 joules or 60 kilojoules.